Hello friends, welcome back again to my channel. Hope you all are doing great and are enjoying my sessions. If you find my sessions to be useful, please don't forget to like, share and subscribe to my channel. Okay, let's start with our fourth session. Today the topics will be units of power and comparison, noise floor, signal to noise ratio, RSSI, uh, then fade margin or SOM. Okay, let's start. Friends, before starting, I'm again telling you if you have any doubt or difficulty or any suggestion, you can freely ask me in the comment section. I will be glad to reply. Okay, so let's start. First, start with the previous session quiz question. So, very first question was which of the following statements are true about amplification? So, as we discussed, amplification is the increase in gain, or I would say increase in strength of the signal. So there are two ways to increase the amplification. One is through passive gain or other is through active gain. So amplifiers are active source of active gain, antennas are passive gain amplifier that focus. So antennas are, yes, these two are option. Then third, signal strength may passively increase because of multipath. Like we discussed, because of reflection multiple paths will get created, and because of creation of these multiple paths signal reach at the receiving point at the same time and helps in gaining the signal up fade, which we call the up fade. So these three are the right answer. Okay, when an RF signal bends around an object, this propagation behavior is known as what? So as I clearly mentioned, difference between diffraction and refraction. Diffraction is bending of a signal when passing through some medium. Diffraction is bending because of some bigger object. So diffraction is the right answer here. Third question. So friends, I did one mistake while putting this question. I forgot to put blank, so I have corrected that mistake in my answers now. When the multiple RF signal arrive at receiver at the same time and are dash with the primary wave, then result can be dash of the primary signal. So out of all the options, if you only possible option is 180-degree out of phase, then it result in nullifying or cancellation. So the F is the right answer for this question. What are some objects or material that are common causes of reflection? So friend, this question seems to be very simple, but actually it's very tricky because different there are many material which do a different phenomena with their parts. Like water, it do absorption as well. So here it as a lake, when it's a bigger material, big water resource as a lake, so they do reflection as well. So you have to be very clear while selecting the option. So objects like metal, definitely asphalt road are bigger ones, and they are smooth, so they definitely do a reflection. Trees, because tree has a hollow space in between, so reflection is not 100% possible through trees. Same way carpet floors again is not the right answer. So metal, asphalt road, lake are the right answer for this question. So now we are going to start our today's session. So units of power and comparison. So you all have heard about watt, milliwatt, all these things, decibel, decibel to milliwatt, all these things you have heard. What is the significance of these units in your RF? What is the significance of these units in your Wi-Fi? So it's very important and very much required to understand the basics of these units, because when you deal with Wi-Fi, these Wi-Fi actually work in a millivolt, and the millivolt is 1000 of a volt. So the exponent is highly high, and you have to understand these units so that you can calculate and design the solution perfectly. Small change or a small mistake led to a drastic impact on your Wi-Fi. So it's very important to understand these units and also to understand its comparison. So in actual, there are two type of units we dealt with. One are actual units, other are relative units. Actual units are units which are known or easy to represent, or I would say have a definite set of value, like a feet, 1 feet, 1 centimeter. These are actual units. They are representing us known or set values. Relative units are units which are not the actual units but are comparable units or relative units and does not represent any set values. So these terms, I know these terms are a bit technical and you would not be able to understand what I actually mean to say. So for this, I have included this analogy in our video. So for example, this is a man, his height is 6 feet. So his height is 6 feet. When you say 6 feet, 6 feet is a known or set value or actual unit. So it is a actual representation or unit of power or actual unit. But when I have to be explain the height of his daughter, I would say his daughter's height is 3/6 of his height. So instead of saying 3 feet, I'm saying his daughter's height is 3/6 of his height. So I am comparing his daughter height with him, not with the actual known or set value. So comparing something with the comparative value is known as relative units. So instead of comparing some known or set value, we are comparing with the some other other value or other reference. So in terms of Wi-Fi, instead of comparing a direct power, we are comparing the power with another source or another power information that is called relative units. Okay. So difference, what is the actual difference? So I have segregated and prepared one table for your easy understanding and knowledge. What is the difference between power and comparison units? So power are actual unit, comparison are relative units. So units, it is units of power, it is used to measure transmission and received amplitude. So transmitted power is 100 milliwatt, received amplitude is I would say 10 dBm. All these are actually measured units of power. But when we do a comparison, I would say loss or gain, how much amount of loss happened while passing through this path, how much gain I have received while through this antenna. So these are units of comparison to actually measure the amount of loss relative, because this loss or gain is relative. This is not actual loss or gain on this path. This gain or loss is a relative loss particular to the incident signal or reflected signal. So it is always a relative one. It is an absolute power measurement, it's a measurement of change in power. Then we will discuss the actual units of power and units of comparison. There are major three units on actual units and three comparison units which we deal in Wi-Fi, which we actually dealt in Wi-Fi. So we will discuss all these six in our coming slides, so you will get a better idea what is the significance of each of these units. So first we will discuss about units of power. So what? A watt is a basic unit of power. 1 watt is equal to 1 watt is equal to 1 ampere of current flowing at 1 watt. So a watt is a name given after a scientist James Watt, who has invented this unit. So this unit is actually the basic unit of power. So it is the reference. And millivolt, when we say that a milliwatt is 1000 of watt. So in our 802.11, generally all the equipments are represented in milliwatt, because there are very rare equipment, or I would say particularly in access point or RF Wi-Fi level, there is no AP or other unit who transmit in watt. So we generally dealt in milliwatt only. Okay. So to for the analogy of watt, if you have to be understand more in a watt, take an example of a water hose at your home. Like this water hose, using that water hose, what you do, you own that water hose. Once you own that, is it, the pressure start coming out of that hose. There is a water flowing out of it. Because of that pressure, if you are putting that pressure and on some point, it will remove the dust from that particular area. So what you are doing, you are applying a pressure of water. As you increase the pressure, that it will impact more, and the amount of water will increase, then also it will impact more. Same way, 1 watt is equal to 1 ampere of current flowing at 1 watt. So either you increase the uh, ampere, or you will increase the volt. So either which way will increase, that watt will increase. So this is the analogy to watt, but you need not to go in that much detail. This is just to understand what you are dealing with. So watt, then milliwatt is important, because all the major 802.11 equipment work on milliwatt only. The third one is decibels to milliwatt. So we will discuss on this after discussing our units of comparison, because this is something related to units of comparison. So first we will discuss units of comparison. So units of comparison, decibel. A decibel is a relative expression and measurement of change in power. So decibel is derived from the word bell. So what happened? Employees at Bell Telephone Laboratories needed a way to represent power losses on telephone line as a power ratios. So as I said, if you have to be represent some values in milliwatt, it is very difficult to represent 0001.00.1 or 10000 something like this. It is easy to represent. It is sorry. It is difficult to represent. It is difficult to understand. It is difficult to memorize it. So what they have done, they have found, they are looking after for some representation way to represent losses or gains in power telephone line. So they defined a bell as a ratio of 10 to 1 between the power of two sounds. So what it actually means, so what they have done, so let's understand this relationship. For example, AP transmit at a power of 100 milliwatt or 10 raised to power 2, and laptop receives the signal from AP at power level of 10. Then the ratio between two of these is 10. This 10 raised to power 1 is equivalent to 1 bell. So the power of 10 is equivalent to the power of is equivalent to the bell. If 10 raised to power 2, then it's 2 bell. If 10 raised to power 3, then it is 3 bell. So 10 raised to power 1 is equivalent to 1 bell. So here laptop received power is 10 milliwatt. So this is a bell. Now what is decibel? Decibel is 1/10 of the bell. So if the power if the ratio of bell is 1, then 1 bell is equivalent to 10 decibel. So you are deriving a decibel from bell, so that's why it is called bell. Decibel is derived from the word bell. So there is a one I have prepared one table for your easy understanding and memorizing this part. So if the power is in milliwatt, 10 raised to power 3 or 1000 milliwatt, then you would say it's 3 bell, and in decibel it is 30. If it is in minus or 10 raised to power minus 2, or you would say 0.001, then it's 2 minus 2 bell or 20 decibel. So this is a decibel. Okay, so going ahead now, there are two other units of comparison or relativity. One is decibels isotropic and other is decibels dipole. What it what do you, what I when I say decibels isotropic or decibels dipole, so with the word isotropic, I think you got some idea with the isotropic radiator, so which we discussed in last video. So exactly. The decibel iso dBi, decibels isotropic, the gain or increase of power from an antenna when compared to isotropic radiator. So isotropic radiator, you all know that isotropic radiator is a reference wherein you would say it's a zero, which are often referred to as zero, or I would say baseline. So when you measure the gain or power of antenna compared to that isotropic radiator, then it is called decibels isotropic. Okay, so the dBi value is measured at the strongest point or the focus point of the antenna signal only. Dbi value is always positive, never been a negative. It can be zero, but when you say that antenna with a dbi value at of zero, then it is referred to as no gain or unity gain antenna. Okay, so 802.11 antennas are typically measured in dbi. So you will see we will use out of this after in coming videos, the most of the your data sheets of your vendors, most of the presentation, it will be in dbi or dbm only. So a antenna are typically measured in dbi, and transmit or receive power will be measured in dbm only. So you will find this throughout the Wi-Fi. You will find it throughout these videos. You will find it in coming videos. So very rarely other measuring as measure units, whether it's a relative, whether it's a actual units. So only two are majorly used: dBm, which is actual unit of power, and dBi, which is a relative unit of comparison. So you will find these two units to be used widely. Then decibels dipole. So same like decibels isotropic, the gain or increase of power from antenna when compared to single signal of dipole antenna. So the most common type of antenna used in access point is half wave dipole antenna. Okay, so these, when you compare or the increase, when you measure the gain or power of antenna as compared to that signal of dipole antenna, then it is called decibels dipole. Same like decibels isotropic when you compared it with the isotropic radiator antenna. So now what happened in antenna industries, as I said, you will use maximum for a relative unit you will use dbi, for actual unit you will use dbm. So what happened if you have a one antenna with the dbd value, which is decibels dipole, and other is a dbi value? How you would be able to convert it into dbi, or how you would be able to uh, understand what is the actually dbi value or dbd value? So a so answer is here: a standard dipole antenna has a dbi value of 2.14. So if you have some dipole antenna with the like a 3 dbd or 2 dbd, what you have to be do, you just have to be add this 2.14 into it, and you will get dbi. So it will get converted into dbi, and you can easily use it as a dbi in your calculations, in your comparison. So because majorly used is dbi only. So this is an example. To convert 3 dBd into dBi, just you do 3 plus 2.14, it will comes to be a 5.14 dBi. Any value, any gain which you have in dBd, just add 2.14 in it, it will give you the output of dBi. So now we discuss three type of relative units. First is decibel, which is derived from bell. Other is dBi. Third one is dBd. So I have again prepare a one table for your easy understanding the difference between these three units. So decibel is derived from word bell, as we saw it. dBi, it is comparison with the isotropic radiator. dBd, it is a compared with dipole antenna. Then decibel can be positive or negative. dBi is always positive, and same way decibel is also positive or either zero. It cannot be negative anyway. Then decibel is lesser used. dBi is the most widely used, and you will find it referenced and everywhere. Then the third, dBd, is very rarely used, and you can't find very much of dBd in your throughout Wi-Fi studies and through your calculations. Okay, so friends, as we have as I said, we will discuss dBm after this relative units. So why dBm? actually, okay, decibels to milliwatt. So why I said, because decibels to milliwatt is in either way, I mean, it's bit compared to the decibels, decibel dBi, decibel isotropic, or decibel dipole. So same way the name dBm comes from decibels only. But why it is considered as actual unit instead of relative unit? Because dBm provides a comparison, but it provides a direct comparison with the signal. Instead of comparing a signal to another signal, it is a providing a direct comparison. Like, it is used to compare a one signal to 1 milliwatt of power. So as dBm compares the absolute value instead of relative signal, it is considered as unit of power and not unit of comparison. That is the whole difference, because it is comparing directly with the unit of power. So 0 decibel to millivolt is equivalent to 1 milliwatt. So this is the baseline, or I would say this is the comparison of decibel to milliwatt, and that's why it is considered under actual units of power. And we discussed two things, as I'm again telling you, dBm to dBi. There are two major units which we are going to use throughout our study or throughout our Wi-Fi curriculum: dBm and dBi. dBm is actual unit, dBi is relative unit. The only difference between dBm and dBi is that sorry, there are two differences. First difference is that dBm is actual unit, dBi is a relative unit. The second difference is that dBm can be negative, but dBi is always positive. So friends, make sure whenever we are discussing, so do always keep this in mind. dBm can be negative, but dBi is always positive, because it's a gain. So it's always a gain or focus. It can be zero but never in be negative. So going ahead, like we discuss all this. So we have done comparison as well. So friend, this is very important topic. So as a CWNA, you don't need to go into log calculation or logarithmic calculations. Yeah, sure. Of course, when you are a product engineer or you are developing something, then definitely you have to be understand logarithmic. But as a administrator, as a solution architect, as a designer, or as a normal Wi-Fi site survey, you need not to understand these logarithmic values. But yeah, definitely you want to calculate the loss, gain, and everything while designing the solution. So for that, there is a rule called rule of tens and threes. So using that rule, you can easily calculate the gain and loss while in your communication. So what is this rule? This is very important, and from examination point of view, from CWNA point of view, from your Wi-Fi implementation point of view. So if there is a loss of 3 decibel, then power will decrease by half. If there is a gain of 3 decibel, then power increased by it would be power increase 2 times. If there is a loss of 10 decibel, then power decreases 1 by 10th. If there is a gain of 10 decibel, then power increase 10 times. So this is a rule, very simple and easy to memorize. You have to be keep that rule in mind always to proceed and to calculate your values of Wi-Fi, to calculate your loss, to calculate your receiver sensitivity. So like we will proceed further on this video, you will see there are a lot of things: RSSI value, signal to noise ratio, receiver sensitivity. So these are the values which you have to be calculate for perfect design and for implementation. So for this implementation, you need to calculate all these values of free space, path loss, any other loss on in your network. All these losses has to be considered. So but as an engineer or network administrator, you need not to do logarithmic calculations. So but you have to do calculation, and to do these calculations, these rules are defined. they would not these rules would not give you a exact 100% accurate value, but they will give you a value accurate up to the requirement. So these are the values globally or widely used by all the WLAN engineers. So let's see with an example of how these rules will be implemented. So this is one transmitter. Okay. This transmitter is transmitting power of 100 milliwatt. Okay. Now there is one connecting cable. This connecting cable has a loss of 3 decibel. So as we discussed, if there is a loss of 3 decibel, power will become half. So now power comes to be 50 millivolt only. Now here comes antenna. Now antenna has a gain of 10 decibel, 10 dBi. So friends, see, all other things are measured in connecting cable in dB or dBm. Antenna gain is measured in 10 dBi. Okay. So with the rule, 10 decibel is multiplying your power 10 times as per the rule. So what happens? Your with the antenna gain, your power becomes 500 milliwatt. Now we know that there is a free space path losses. So if your space path losses is again minus 10 decibel, then what happen as per the rule? It will 1 by 10th your power. It will give decrease your power to 1/10. So power comes to be 50 milliwatt only. Now at the receiving end, antenna is there. This antenna has a gain of 3 decibel. So with the rule of tens and 3, so with the 3 gain of 3 decibel, your power becomes 2 time. So now the power comes to be 100 milliwatt. Again there is a loss of 3 decibel because of this connecting cable, and as per the rule of 3 decibel, your power becomes half, again 50 milliwatt. At the receiver, you will get 17 decibel to milliwatt your as a receiving power, and the power for the received receiver is 50 milliwatt. Okay, so this is your calculation, this is the standard rule, and when you will find a one or two question as well in your CWNA exam with respect to this only. So this is very important for your calculation, this is very important for your solution design. So please do practice this rules of 10 and 3. If you have any doubt, please share your comments. I will be more than happy to reply you back on this. Okay. So now friends, moving ahead, this is we discussed about RF mathematics generally, and now measured units of power measurement. Now we are going to discuss about noise, SNR, noise. What is noise floor? So it is background level of radio energy on specific channels. So like we are in a some pub, and me and my friend are standing a bit far from each other. I'm yelling to my friend, hey Rahul, hey Rahul. So he would not be able to listen if there is a huge lot of crowd in between and they are also dancing and there is a lot of music going on. So there is a lot of noise in between, so I'm not able to speak to my friend and he is not able to communicate with me. So that is a noise floor. So this is a noise at particular, because there are a lot of other persons who are talking in between. So at the same channel or at a specific channel there is a lot of noise. So noise happen in two ways. One is through modulated or encoded bit. This is a background noise transmitted, like my AP is installed in one room and there is another AP installed in the nearby vicinity, and that AP is also working on the same channel at which my AP is working. So there is a background energy which is coming or interfering in my signals. So this is a background energy or modulated interference or modulated noise. So this is an example, two APs which are placed nearby and both are working on the same channel, so they are interfering. And the other one is unmodulated. Unmodulated interference or noise is one which occur when 80 known 802.11 devices uh, that noise comes from non 802.11 devices such as microwave oven, because microwave and Bluetooth are working in same at almost same frequencies at which 802.11 devices are working. So it generates background noise for in our specific channel. So this is a noise floor. So noise floor is not important, but this is important for your understanding to understand further noise to signal ratio and all this point. So next is noise to signal ratio. So actually it is not a ratio, it is actually the difference in decibels between the received signal and the background noise level, and it is not a ratio. So it's a difference, but it is represented like a signal to, it is written as signal to noise ratio, but in actual it is a difference. So an SNR of 20 decibel or greater is considered a good quality, and SNR of 10 decibel or lower is considered a very poor quality signal quality. So while designing your solution, do do remember that thing, that you should keep a SNR of 20 decibel. How you will calculate your SNR? Let's see it an example. So if you have an received signal amplitude of 85 decibel millibaud, and your noise level ratio is of noise level is of minus 100 decibel to millibaud, then your signal to noise ratio is 15 decibel millibaud. So make sure that you have an understanding of your received signal as well as a noise level, so that you can accurately calculate your SNR ratio, and then you can plan and design your solution accordingly. So this is very important while designing, because uh, a little fluctuation can result in data corruption, because uh, with data transmission can become corrupted with very low SNR. As your SNR goes less than 10 decibel, it is very evident that data will get corrupted, because if the amplitude at the noise floor is too close to the amplitude of your received signal, data corruption will occur, and you have to be the retransmission at layer 2. So this retransmission has an impact, a huge impact on your services. So make sure you have calculated your signal to noise ratio. So now friends, as we discuss signal to noise ratio, now the other important is receiver sensitivity. What is receiver sensitivity? So take an analogy of a human ear. I'm sitting here and I'm listening a lot of sounds, like it's night. If you can say, take an example of night is quite silent, and you can listen a click of your clock, you can listen mosquitoes whistling around your ear, so you can listen these sounds. But if you are in a day, there are a lot of other sounds you would not be able to hear, click this clock click and any other small sounds. So your sensitivity will increase, or your sensitivity, I would say, the receiver sensitivity is the sensitivity at which receiver can receive or detect an RF signal. So the lower the sensitivity is, the best the receiver is working. So if I can listen a lower sensitives at the lowest power level, then I am very good receiver, and I can listen even a very small signal which are coming to me. So receiver sensitivity should be as low as possible. i mean I mean possible in the sense, receiver sensitivity as lowest as possible, it means it is able to listen to the lowest power level. The lower the power level that the receiver can successfully process, the better is the receiver sensitivity. Okay, next is RSSI. So RSSI is receive signal strength indicator, or it is measure of power level that a RF device is receiving from the radio infrastructure at given time and location. So measure of power level that a RF device is receiving. So it's the same or little bit related to receiver sensitivity only. Mm, In Wi-Fi, actually it's not that important. I mean, it's important, but from implementation, every vendor is using RSSI metric in a proprietary manner. The actual range of RSS value is 0 to 25, and as a vendor A, I can take a start from the range 0 to 255 and take 0 as minimum and 255 as maximum. As a vendor B, I can take 255 as minimum and 0 as maximum. So there is very huge ambiguity while using this RSSI metric, because every vendor has its own proprietary implementation and there is no guideline given by IEEE for this. But yeah, so RSSI is used. RSSI is used for two major purpose. One is for roaming and other is for dynamic rate switching. Like you define vendor use RSSI threshold to to roam the user from one AP to other AP. If this value goes less than this threshold, it will move the user from that AP to another. Other is used why it is process DRS. Other purpose for which RSSI used is dynamic rate switching. So what is dynamic rate switching? It is a process used by 802.11 radios to shift between data rates. To shift between data rates like 54 Mbps, 30. So to switching between these data rate is done through dynamic rate switching, and it is achieved through this RSSI. Now, link budget. So link budget, why what is link budget? Definitely we will discuss why link budget. What is the benefit of using that link budget? We discussed receiver sensitivity, we discussed signal to noise ratio. All these are interrelated. So link budget is the calculation of all the gains or losses from transmitter to till receiver. Like from transmitter, signal goes through connecting cable or connectors, then it goes to antenna, then antenna passes it to the receiver antenna passes it to the connecting cable, passes it to the receiver through the connecting cable. So there are a lot of losses in between, there are a lot of amplifications in between. So the calculation of all these losses and gain through a path is called link budget. So link budget is the sum of all gain and losses from the transmitting radio through the RF medium to receiver radio. Calculation include all gain and all losses. Okay, so this is one example. To transmit power 20 decibel to milliwatt, connecting cable, loss is minus 3 decibel. Again antenna, then free space path loss, then antenna. So at the receiver end, the received power is 70 decibel to milliwatt. So calculation of all these losses and these is link budget. Why it is important? So if why it is important will help will give this fade or system operating margin will let us know why it is important. So like I explained that received power is 17 decibel to milliwatt. Now as explained, there is one point in previous slide, just that the receiver sensitivity. For example, my receiver sensitivity is 20 decibel to milliwatt. Okay, and I received a signal at 17 decibel to milliwatt. Then I would not be able to listen because the signal is below the threshold. Receiver sensitivity is receiver is not able to listen, and it would discard that signal, or it would not be demodulate that signal. So the receiving signal should be higher than my receiver sensitivity, or equal, at least equal to my receiver sensitivity or receiving threshold, else it will get discarded. So fade margin is buffer or margin of error for received signal to provide link reliability. So while designing a solution, if you have a receiver sensitivity of minus 60, minus 50, minus 40, minus 30, keep some margin, keep a signal. You would say instead of minus 30, you would mention my receiver sensitivity is minus 50 or minus 55 at lower level, that I would not be able to listen at minus 55 or 50, because while transmitting there are a lot of fluctuations or changes in weather, or there, because of these fluctuations or changes in medium, your signal will fluctuate. You would not be exactly getting a signal at the same receiving sensitivity. So if you receive right now, you are receiving a signal at that sensitivity, but later on, because of changes in weather or their increase in free space path loss, the signal received signal goes beyond below the threshold. Your signal will start getting discarded. So always, as a good solution designing, or as a good solution architect or a good WLAN engineer, you should keep some buffer or margin. So this buffer or margin for receive signals to provide link reliability is called fade margin or system operating margin. So let's see one example. So there is, if a receiver sensitivity is minus 16 decibel to millivolt, a transmission is successful as long as the received signal strength is greater than or equal to minus 60 decibel to millivolt. The problem is that signal received fluctuate because of many outside influence such as interference and weather condition, like I explained to you. So because of these received fluctuations, external fluctuations, your received signal strength may decrease, and because of this decrease, your signal your receiver would not be able to receive and demodulate that signal. Let's see. Access point transmitting plus 20 decibel to millivolt power. Because of free space path losses, there is a loss of minus 73.98 decibel. And there is a antenna inbuilt in your laptop, and because of this integrated antenna, there is a gain of 2.14 dBi. Then total final signal at receiver is minus 51.84 decibel to millivolt. Now your receiver sensitivity is 6 minus 60 decibel to millivolt. Here the received signal is minus 51, so it's higher than your receiver sensitivity. As it is higher than your receiver sensitivity, then signal received successfully. Now take a other example. Your receiver sensitivity is minus 40 decibel to millivolt. Here the received signal is minus 51, so this received signal is lower than your threshold. So what happened, as the received signal strength is lower than the receiver sensitivity, the communication will be unsuccessful. So it's very important for you to, while designing the solution, that you should keep some margin or buffer so that your links can reliably work upon. Okay friends, we are done with today's session. As we always do, so now we are proceeding towards our quiz. Then after and this quiz answer again we will provide in a next session. So what RF component is responsible for generating the AC signal? Antenna, receiver, transmitter, transponder. The sum of all the components from the transmitter to the antenna, not including the antenna, is known as what? IR, isotropic radiator, EIRP, intentional radiator. Select the absolute power units of power. So do remember there are two, absolute and relative. So you have to be select only absolute. Then 323 dBm is equal to how many millivolt? So please use 3 and 10 of rule of 3 and 10 and find out the answer. So thanks friend, thanks a lot for today's session. Please don't forget to like, share, subscribe and comment on my video, and please feel free to reach me out in comment section if you have any query or suggestion. Thank you, thanks a lot.